Hello students, welcome to Educate. We are going to continue with chapter number 4 of class 12 physics. So our topic is circular current loop as a magnetic dipole. So we have already derived the expression B equal to mu naught I r square divided by twice of x square plus r square whole power 3 by 2. If you don't remember, I can make you recall this is circular loop on its axis at this point. At this point, magnetic field we can find if this distance is x, its radius is a, etc. So that thing. Here, radius of the loop is taken as r, so just take it r, and it carries current, say I, then magnetic field can be found. Now, they are saying that if this radius is very less as compared to the distance of the point where magnetic field is to be found, means x is greater than r, then in denominator we can ignore this r. So what do we get? We get B equal to mu naught I r square divided by 2x cubed, right? Now, note that the area of the loop is pi r square, right? So we can write B equal to mu naught I. We can insert pi in denominator and numerator so that area may be included. So we just write here pi and pi, right? So here pi r square will become area. So we will get this mu naught IA and in denominator 2 pi x cube, correct? As earlier, we defined the magnetic moment M to have a magnitude IA. If you remember, I told you M is given by I times A, where A is the loop of the area, I is the current in it. So M equal to IA. So in place of IA, we can write M. So we get this relation, B equal to mu naught M divided by 2 pi x cube. Is it okay? Or we can multiply it by 2. So in numerator it will become mu naught times 2m divided by 4 pi x cube, right? Here equation, if we change it, here they are saying that suppose we want to go into electrostatics. So for that we have to replace mu naught by 1 upon epsilon naught. Then we will see that electric field due to dipole will be given by this, because we have replaced M by PE, electrostatic dipole, M was magnetic dipole, sorry, and B is replaced by electrostatic field. So we have got the relation that we have already derived, that electric field due to dipole on its axial point is given by twice of magnetic dipole moment divided by 4 pi epsilon naught x cube, where x is distance from the pole, right? It can be shown that the above analogy can be carried further. We had found in chapter 1 that the electric field on the perpendicular bisector of the dipole is given by this, right? So similarly, if we talk about magnetic field, then analogy, as you know, that epsilon naught will be replaced by 1 upon mu naught. So we will get this relation, B equal to mu naught M divided by 4 pi x cube. Situation, this is the case when x is greater than r. I think you have understood it fully. Now, this result gives the results given by this and this two equations become exact for a point magnetic dipole, means magnetic dipole of small size. So the results obtained above can be shown to apply to any planar loop, right? A planar current loop is equivalent to a magnetic dipole of dipole moment M equal to IA. This is important. You have to understand and some numerical questions will be given to find magnetic moment. If R is given, I is given, in that case how will you proceed? You will find M equal to I times pi R square, right? So this thing, so M equal to Ia, which is the analog of electric dipole moment P. Note, however, a fundamental difference, an electric dipole is built up of two elementary units, the charges or electric monopoles. In magnetism, a magnetic dipole or a current loop is the most elementary element. The equivalent of electric charges, magnetic monopoles, are not known to exist. Keep in mind, right? Because in case of dipole, what you have seen, one is positive, another is negative, and they are equal in magnitude. So here, similar thing is not there, like magnetic monopoles don't exist. We have shown that a current loop produces a magnetic field, right? And behaves like a magnetic dipole at large distances and is subject to a torque like magnetic needle. This led Ampere to suggest that all magnetism is due to the circulating currents. This seems to be partly true, and no magnetic monopoles have been seen so far. However, elementary particles such as an electron or proton also carry an intrinsic magnetic moment. Keep in mind, these elementary particles have their own magnetic moments, intrinsic magnetic moments, not accounted by circulating currents. Now we are going to see what is moving coil galvanometer or MCG and what is its purpose, and from there we will try to find out the expression for ammeter and voltmeter. So let's see how. Here, moving coil galvanometer. Currents and voltage in circuits have been discussed extensively in chapter 3, so we know it. But how do we measure them? Let's see this all. So how do we claim that a current in a circuit is 1.5 ampere or the voltage drop across a resistor is 1.2 volt? So they are creating the question that how will you measure, what devices you will use for evaluating current or voltage, etc. So those all things we are going to study here. So figure is given that we will see on next page. The moving coil galvanometer, it is a device whose principle can be understood on the basis of our discussion. So let's see what discussion is given. The galvanometer consists of a coil with many turns free to rotate about a fixed axis. So let's see the diagram first, and then this is galvanometer, right? Here there is scale, this is pointer, here there is coil, here pivot, this is spring, right? Here there is a radial magnetic field, right? Because this is magnet is like this. So in order to maintain uniformity, right, the field is taken to be radial, right? So pointer will always be along the direction of magnetic field, correct? You have seen it, you have understood. The moving coil galvanometer, its elements are described in the text. We will see, depending on the requirement, this device can be used as current detector or for measuring current, and the voltage detector, that is for measuring voltage. So like ammeter or voltmeter. So we have to convert this into ammeter or voltmeter, that we will study soon. But before that, let's read some basic points, and after that we will analyze. So here a galvanometer consists of a coil with many turns free to rotate about a fixed axis. In a uniform radial magnetic field, there is a cylindrical soft iron core which not only makes the field radial but also increases the strength of the magnetic field. So here you should know what is purpose of cylindrical soft iron core, right? Then when a current flows through the coil, a torque acts on it. This torque is given by tau equal to NIAB, that you have already studied. Here N is number of turns, I is current, A is area of the loop, B is magnetic field. Now, so everything is clear? Where the symbols have their usual meaning. Since the field is radial by design, we have taken sin theta equal to 1, means theta will be 90 degree. in the above expression for the torque. The magnetic torque in IAB tends to rotate the coil, right? When torque will act, then there will be a counter torque which will try to prevent it from moving, and that will depend on angle moved. So we can say counter torque is K phi, and this torque as we have calculated in IAB. So both torques will be equal. So if they are equal, then we can find the expression for this deflection, angular deflection. So phi will be equal to NAB divided by K times I, right? So here this term is galvanometer constant, and NAB divided by K times I. You will get some questions. We can write it something like K or any other factor we can use, but it's not necessary. Or here one thing we can do, if we want to check that this deflection is proportional to I, right? Because this is a constant. So we get this relation, more deflection means more current is there. So that's it. The galvanometer can be used in number of ways. It can be used as detector to check if current is flowing in the circuit. We have come across this uses in the Wheatstone bridge arrangement. In this uses a neutral position of the pointer when no current is flowing through. Galvanometer is in the middle of the scale and not at the left hand. So it will become in the middle, right? Okay, so here before studying galvanometers, use of galvanometer as ammeter or voltmeter, we are going to see some more relations based on it, like current sensitivity, voltage sensitivity. So two factors we will see, and after that we will come towards ammeter and voltmeter. So here phi upon I, we find phi upon I is called current sensitivity, equal to NAB divided by K. It's obvious from here if you divide by I. Now, if you want to find voltage sensitivity, so current sensitivity, here one more thing, you can just divide by resistance also. So it means phi, when phi is divided by voltage, we will get voltage sensitivity. It means phi upon IR will be equal to NAB upon KR, right? So here same thing is explained, that phi upon V equal to NAB upon K I upon V. So NAB divided K, here R is also there, right? So one very important point, that if current sensitivity increases to double, then will voltage sensitivity also get doubled or not? So answer is no. Here logic is explained, and you have to read it carefully, because this question is also asked in exam. An interesting point to note is that increasing the current sensitivity may not necessarily increase the voltage sensitivity. Here in previous example, previous equation, we are putting N equal to 12, right? It means we are doubling the number of turns. Then what will happen? So phi upon I will become double. So twice of phi upon I. Thus the current sensitivity doubles. However, the resistance of the galvanometer is also likely to double. You are making more turns, so resistance will also get doubled. Since it is proportional to the length of the wire, of course, then when N gets doubled, R also gets doubled. So when we find voltage sensitivity, so it remains same, right? So it is not necessary that increase in current sensitivity means increase in voltage sensitivity also. Now we are going to see how to convert the galvanometer into an ammeter. So galvanometer to ammeter, right? So what we do, we take this galvanometer here, and suppose I current is coming. At this point we connect another parallel resistance, say it is S, called shunt resistance. So what happens? Ig current will pass through the galvanometer and remaining I minus Ig will pass through shunt. Now here if we apply KVL, Kirchhoff's voltage law, what do we get? Here if we move in this direction, if you remember, and like this, so what do we get? We will get I minus Ig multiplied by S minus resistance of galvanometer is to be taken as G and it is carrying current Ig. So Ig times capital G equal to 0, or I minus Ig times S is equal to Ig times G. What is our concern? Our concern is to find out the shunt resistance, the resistance that is used in parallel. So S will be equal to Ig into G divided by I minus Ig. Since value of Ig is very small as compared to I, so for calculation purpose, we will remove this Ig. We will do the calculation by formula S equal to Ig times galvanometer resistance divided by I. Just we will use this one. I think you have understood. Now we are going to see how to convert a galvanometer into a voltmeter. So this is galvanometer, and here we connect a series resistance, say R, and suppose we want to find out, say, voltage range is say V, then and suppose current Ig is flowing through the circuit, then applying KVL for closed loop. So V equal to Ig times resistance, this plus resistance of galvanometer. Here our concern is what is value of this R. So for this will become V upon Ig, then minus G will give R. So this formula we will make use while evaluating the resistance to be connected in a series with a galvanometer to convert into a voltmeter. Correct? So you have understood. Now, so let's see the question. Here there is one question based on these concepts. In the circuit, the current is to be measured. What is the value of the current if the ammeter, this ammeter shown is a galvanometer with resistance of 60 ohm. Suppose it has resistance 60 ohm. Then what do you observe? This is 3 ohm, this is 60 ohm, voltage source is 3. So current you can easily find I equal to 3 divided by 63 ampere. Correct? Now, second situation, it is a galvanometer described but converted to ammeter by a shunt resistance R 0.02. Now what will happen? If there is shunt resistance, this is converted, then what happens when galvanometer, suppose simple example I am telling you, suppose this is galvanometer and its resistance is say 15 ohm, and if suppose 1 ohm resistor is connected in parallel with it, then equivalent resistance will be less than 1 ohm. So here shunt resistance is given 0.02 ohm. It means total resistance of this will be negligibly small, right? And third case we will see the answer. And third is an ideal ammeter with a zero resistance, so there is no resistance at all. It means it is just simple conducting wire. In that case, directly we can find 3 volt and 3 ampere. Correct? So let's see the solution. Total resistance in the circuit, first case as I told you, it will be Rg plus 3, that is 63 ohm. So I will be 63, 3 upon 63, that is 1 upon 21 or 0.048 ampere. And second case, as I told you, so it will be very less resistance, that will be negligibly small. So 60 into, if you have not understood, so you can understand it that what is happening. So this is happening like this. This is suppose 3 ohm, and here in case of ammeter was having 60 ohm resistance, this galvanometer, and it is connected to 0.02 ohm in parallel. To convert it, this was galvanometer. To convert it into ammeter, we have connected 0.02 ohm shunt resistor. So effective value of this will be almost 0. It will be less than 0.02, but we are taking 0.2, right? So total resistance now 3 ohm is this, 0.02 ohm is this. So 3.02 ohm. And voltage, as we have seen that it is connected to 3 volt battery. So 3 divided by this will give 0.99 ampere. And if it is ideal ammeter, then this galvanometer will we have like a simple conducting wire with no resistance. So forget it. Just 3 ohm resistor will be considered, 3 volt battery will be considered. So obviously it will be 1 ampere. So I think you have understood the question. Now we are going to read the summary ones, and then we will assume that you have understood the lesson fully. The total force on a charge q moving with a velocity v in presence of magnetic and electric field B and E respectively is called the Lorentz force. It is given by the expression F equal to QVB. Do you remember it? We have studied about it, that F equal to QE, this is in electric field, and F equal to QVB in magnetic field, but both here we write FB, this FE. So when both fields are present in that case, total force will be combination of the two. That is why F equal to Q, V cross B plus E. Correct? And if you want to find out the direction, so direction of V cross B will be same as that of E or that of F. Correct? Now, and you can work out by using cross product of vectors. A straight conductor of length L and carrying a steady current I experiences a force F in uniform magnetic field, and that is given by F equal to BI-L. I think you remember. And this is length of the conductor, which is inside the field, and B is magnetic field, I is the current. In a uniform magnetic field B, a charge Q executes a circular motion. We have studied about it, and its frequency is called cyclotron frequency, and that can be easily evaluated. If you don't remember, I can make you recall it, how to get this, what we are talking about. We are saying that what is situation if field is means velocity of a charged particle and magnetic field both are mutually perpendicular, then F will be QVB, sin theta will become 1, and this QVB will provide centripetal force. So QVB equal to mv square upon r. From here we can get the value of V, right? And then since we want to find out frequency, so in order to find frequency, what should we do? We can find time period. Time period will be equal to 2 pi r divided by V, and just invert it to get frequency. So that thing is written here. This is a nu C, cyclotron in circular motion, right? So here what do you observe? Does it depend on radius? No, radius term is not involved. This fact is explained in a machine like cyclotron, which is used to accelerate charged particles. So here in your syllabus it is not there, but later on in higher classes you will study about it. Then comes Biot-Savart's law. If you remember, due to a current conductor, at any point we can find magnetic field, and that is given by the formula dB equal to mu naught upon 4 pi I dl sine theta divided by r square. In vector form, it becomes dv equal to mu naught upon 4 pi I dl cross r divided by r cube. And if we want to find out total magnetic field, then it can be integrated and we can get, right? Then the magnitude of the magnetic field due to circular coil of radius r carrying a current I at an axial distance x from the current is, we have already seen these expressions, but for making you remember things, I am just telling one by one. So B becomes mu naught I r square divided by 2x square plus r square whole power 3 by 2, and I at the center, it means what happens when we talk about the center, it means we are assuming that the distance of that point is 0, means we have considered the axial point. If you remember, the situation is like this. First we are considering at this point, and now we are making x0. If this term vanishes, in that case we will get this relation. Then comes Ampere circuit law. If you remember, closed line integral of magnetic field equal to mu naught times current enclosed by the loop, right? And if length is different, like suppose you have a conductor, so this integration dl will give L, so we can find the magnetic field. So it will be equal to mu naught I divided by L, and then further we can include the number of turns, etc. So we can get final result. Then the magnitude of the magnetic field at a distance r from a long straight wire carrying current I is given by. So this is another important result, that if you are given an infinite long wire and you want to find out magnetic field, suppose this is infinite long wire, it carries current, and at distance r you want to find out magnetic field, then B is given by mu naught I divided by 2 pi r. So this thing you have to memorize. And here what happens, the field lines will be like this, concentric circles, right? Direction of field, if current is in upward direction, then here field will be perpendicular down, here field will be perpendicular up, etc. So that you can easily understand. Then magnetic field due to solenoid, if you remember, B equal to mu naught Ni, where N is number of turns per unit length. And also you have studied that if there are two parallel current conductors, in that case there will be a force, right? So if this is I1, this is I2, separation is R, then force per unit length you have studied at mu naught I1 I2 divided by 2 pi r. So that thing you have studied. So, and one more aspect you have understood, that if the two conductors are carrying current in same direction, then there will be force of attraction, and if anyone is carrying current in opposite sense, in that case there will be repulsion, unlike the electric charges. Then comes magnetic moment. Magnetic moment, if single turn is there, in that case M equal to Ia. If there are n turns, then it will be NIA, and then we can find the torque M into B, and if theta is given, then we can easily evaluate. Then we have studied about moving coil galvanometer, in which this the torque will be equal to, this will be restoring torque when there is twist in the spring. So you can read it again, and K is called torsion constant. So that you have to memorize, and then you can easily evaluate. Then, as I told you, that moving coil galvanometer can be converted into an ammeter by connecting a shunt resistance parallel to it, and it can also be converted into a voltmeter by introducing a resistance of large value in series with it. So this is all about the chapter. I think you have enjoyed, and there are certain points for you to ponder over. You have to read them, try to find out the result if they have asked certain questions. In next lecture, we will study the numericals based on this chapter. Thank you for watching. Team Educate.